the first day of class and on the syllabus. But just want to make sure, don't go to the ASU final exam schedule. It will say something different than this. It will say that our final is based on the time that we meet. That's not true. Our final is going to be Tuesday night of finals week. Tuesday the 10th, or 2 weeks from yesterday. Don't forget that. Also, our exam number 3 is the Thursday, a week from tomorrow, Thursday after we get back. So I will post, very soon, today after class, I'm going to post the review sheet. It'll be in the same place as usual. Where? So, the review sheet will be exam prep. So just like usual, in exam prep, you'll go there and you will see a exam 3 folder. There'll be an exam 3 folder and it will have the review outline for our exam, which is a week from tomorrow. So definitely don't wait till Wednesday. I will also be posting again some web work review problems for number 2, which is a good way for you to study because you get immediate feedback. Okay. BAC 216. So 316? 316. Sorry, 316. Again, so sometime later today, I'll have exam 3 folder up. In that folder will be a review outline, as normal, as the other exams. Questions?
When is exam 3?
Thursday after we get back, a week from tomorrow.
So there's going to be web work?
There will be web work.
Okay. Is that going to do a final? Is that going to have like some sort of bonus?
Extra credit on exam 3. Just like the web work for exam 2. Okay, and then also in the grade book, I've posted 3 new items for kind of a current grade in the class. One is homework average. One is exam average. This is what the headings are. And then overall 1127. So that overall 1127 is somewhat mostly a current standing in the course. It doesn't include any web work. So it doesn't include the web work bonus, and it doesn't include all the web work in the first month of class. So you can go on to web work and look at your overall average there and compare it to your overall. It might pull that up or down. Okay, it might pull your overall in the class up or down, but this just takes into account paper homework and quizzes and the 2 exams and the pretest. It does include the pretest bonus on exam 1. So that gives you an idea of where you're at in the class. Okay? Questions on that? But there's still lots, so there's still the 3rd exam and the final exam, which is a huge chunk of the grade. So there's lots of room to improve, lots of chance to improve. But that means if you need to improve, that means you've got to start studying for exam 3 soon. Do not wait till Tuesday or Wednesday. Okay, any questions about that kind of stuff? Exam 3 or what was the other thing we talked about? Or grades. Okay, so where are we? Oh, no, I don't want that. I want this. Okay, I want to look at sine again, not arcsine, sine. And let's quickly go through this. This is review. What's the input meaning of sine? What's the input meaning of sine? Better know this. Who's talking? Adam. Okay, and I was not great about this, but measure of the angle. swept counterclockwise from 3 o'clock. That could be in radians, that could be in degrees. Okay, but the input is not the angle. The angle is the object. It's the measure of the angle that is the input. Yeah?
I was going to say, wouldn't it be, in addition to that, to the, well, above the horizontal axis?
The input? No. The input into sine is just the angle swept the angle measure of the angle swept counterclockwise from 3 o'clock. It's how open the angle is. How open the angle is. What are all possible angles that we can put into sine? 0 to 2 pi. Can we put in other angles besides 0 to 2 pi? No, angle. What angle measures are possible for inputs into sine? Okay, can we put in, so for sure 0 to 2 pi. Can we put in angle measures greater than 2 pi? Up to what? We can keep going around the circle. 4 pi, 6 pi, 100 pi, a billion pi. What about, can we have negative angles? Clockwise. Clockwise swept angles give us a negative measure. Therefore, and that was, I heard you over there. All real numbers. That's right. All real numbers we can put in. All right, the output of sine. I think we learned something. Vertical distance above the horizontal diameter in. All right, so now we want to, this is true, but I want to be a little more specific, even more specific than this. Vertical distance to where? Vertical distance to where? Right, it's good.
Vertical distance to the measure of the radius.
But where do we where do we stop? Where is it that determines this vertical height?
Circle to the circle.
Yeah, so the circle, right? So it's where the terminal side intersects the circle. Where the terminal sides to the circle. In radius length. So our whole context was on the circle, so we didn't really specify that. But you'll see in a minute why I want to. So vertical distance above the horizontal diameter up to the circle, up to where that terminal side intersects the circle. What are all possible outputs of the sine? What are the values that can come out of sine? What are all possible vertical distances to the circle in radius lengths? You guys, yeah, eventually we got there, okay? We can be at the bottom of the circle, that's the least, right? Because that's 1 radius length below. And the very top of the circle is 1 radius length above. Okay, now there's this new function, and it's also a vertical distance. It's also in radius lengths. It's also from the horizontal diameter. But there's a difference, so that's why it's a different function. Okay, so it's a vertical distance from the horizontal diameter in radius lengths, but it's not to the circle anymore. It's to the terminal side of the angle on the 3 o'clock tangent line. So on the line that's tangent to the circle at 3 o'clock, we can trace that up to where the terminal side goes, and that's this function. So the vertical distance from the horizontal diameter to along the 3 o'clock tangent. So that's the new thing. So, and then this 3 o'clock tangent is kind of my little slang for it. Just to save words, because we're getting lots of words here. The vertical distance, sorry, above, it's still above. The vertical distance above the horizontal diameter But now, not up to the circle, but along the 3 o'clock tangent line in radius lengths. Okay? And the input is the same. It's the same angle. So let's get a picture of that so you have a visual of that. So here is our circle, and I'm going to sweep the angle counterclockwise, our common angle theta, and do you see that blue? That's the, oh no, is it a circle or not? Please be a circle. Yeah, okay. I hate distorted images. Okay, so I want to turn off the graph paper. There we go. Okay. So that blue line, there's that distance I'm talking about. The distance up to the terminal side along what I'm calling the 3 o'clock tangent, or this vertical line that's tangent to our circle at 3 o'clock. So let's figure out what, if we track, so again, we're going to, like we've done before, so as our angles measure sweeps counterclockwise, over here on this graph, is that angle measure increasing across the x-axis, okay? So so our increasing angle then, we're graphing on the horizontal axis over here, increasing angle. And then on the y-axis, we're going to track this new quantity that we're talking about, the vertical distance above the horizontal diameter, along the 3 o'clock. So we're going to fix right there on the 3 o'clock tangent, and we're going to track that vertical distance along the 3 o'clock diameter. So at theta equals 0, what is this new quantity? What is the vertical distance along the 3? What is it at 0? 0. And then at pi over 4, so what happens between 0 and pi over 4 to that vertical distance? What does it do? It increases. Okay, so this is about pi over 4, which is 0.7, about 0.78. So this is pi over 4 radians, which is like 0.785, 785. So at this angle, what is that vertical distance in radius lengths? What would it be? Y1, Adolka? Yeah, so this is truly the unit circle. This says radius 1. So because we are splitting, by symmetry, we're splitting that quadrant directly in half, that makes that an isosceles triangle. So these two legs are the same. So this is the same as the radius. So at pi over 4, we get okay, sorry. So at pi over 4, this quantity that we're tracking, this new quantity that we're tracking is 1. And in between, so as the angle increases from 0 to pi over 4, what happened? That went from 0 to 1. Now what happens as we go from pi over 4 to pi over 2? What happens to that vertical distance along the 3 o'clock tangent? Dang it. Gosh. Butterfingers. What's happening now? Yeah, it's getting really big. And the closer we get that angle to pi over 2, is what I should do. Okay, here we go. So the closer I get, what happens to that vertical distance on the 3 o'clock diameter? Yeah, it's going to get really big, and the closer we get, the bigger it's going to get. So here, this is just shy of pi over 2. And I have to zoom, look out, I have to zoom way out. So here, I have to even. In order to see that point, I got to change our scale and our axes. So here, I'm at 1.56, which is just shy of pi over 2, and that is 90. So that vertical distance right now is 90. And I could get in even closer to pi over 2, and that thing's just shooting up, right? We've seen this before. What's going on there? So oh shoot. Right. Sorry. There we go. So at 1.57, at pi over 2, here's pi over 2 right about here. As the angle increases from pi over 4 to pi over 2, what does our vertical distance along the 3 o'clock tangent do? It keeps increasing and increasing and increasing. In fact, it increases what? As much as we want it. So you could get closer and closer to pi over 2, and that thing just keeps getting longer and longer and longer. Doing the wrong one, that's the problem. So what about at pi over 2? So when that angle's at pi over 2, what is our vertical distance? Right? It won't intersect. There'll be parallel lines, so it'll never intersect. So it's undefined, right? It's undefined when we reach pi over 2. The length of that's undefined because it'll never intersect our terminal side. So what goes on our graph? An asymptote, right? So we'll have a vertical asymptote of pi over 2. This length is undefined when we get to pi over 2 because it doesn't intersect the terminal side of the angle.
Which one is the terminal side?
Terminal means end, right? Terminal means end. So which one is it?
Red.
The pink, yeah. Yeah, so initial side is the 3 o'clock position. Terminal side is where we rotate to. Okay, so in the first quadrant, this quantity, this vertical distance along the 3 o'clock tangent goes from 0 to as high as you want. And then it's undefined at pi over 2. So let's actually watch that truly happen here. Here we go. Okay. Ready? So this is what we came up with. Increasing to 1, so now it's at 1, and then past pi over 4, it gets as big as you can imagine, as long as you get as close as you can to pi over 2, and then at pi over 2, it's undefined. Okay. Now what's going to happen when we cross over to the second quadrant? Where will the terminal side intersect this vertical, the 3 o'clock tangent? Where will it intersect? What's that? How is that? So can you explain that? How is that possible?
Because the line
Yeah?
goes all the way down, and when you turn to the left, it'll be really far at the bottom.
Yeah, right. Good. All right, so let's watch it. So as soon as we get up there to pi over 2, and then we go a little bit past pi over 2, then we have to extend that line into the fourth quadrant. So there's the asymptote. Can you see the asymptote? So now to get it to intersect the 3 o'clock tangent, we have to extend it the other way. Like you said, we have to extend it down. And so now it's going to intersect at a large negative value. And so then as we increase that angle from pi over 2 to pi, what is the graph going to be like? Negative values getting more or less negative? Getting less negative. It's getting shorter. There's shorter negative values. Until we get to pi. And at pi, what's the vertical distance? Back to 0. I can't get it exactly, but you see that here we are at pi, and it's 0. All right, now what about in the third quadrant? What will happen in the third quadrant? So in the third and fourth quadrants, imagine what will happen. So we're going to keep sweeping this terminal side around the third and fourth quadrant, and we're still measuring the vertical distance along this 3 o'clock tangent. Predict what's going to happen. Go. So talk to the person next to you. Okay, so is this what you thought? Ready? Watch it. So as you go just past horizontal, greater than pi, again, we have to extend it. To get it back, we have to extend it back the other way, and now it's gonna intersect it where that quantity is positive. And as you increase the angle, it's gonna do basically the same thing that happened in the first quadrant, you see? And then what happens when we get to the bottom of the circle? What's it right now? I'm at 3 pi over 2. Undefined, right? They won't intersect. So that's an undefined length. Undefined length until I get into the fourth quadrant. And now that terminal side here can intersect, but way down in negative territory. So that's a large negative value, and as the angle continues to increase, it gets shorter but negative until at 2 pi, back to 0. So that's from 0 to 2 pi. That's what this quantity does. It goes way up, and then suddenly it's negative and comes back to 0, and then it goes way up again to positive. Suddenly it's negative and comes back to 0 in one full rotation of the angle. Okay, so question, what is the period? So this is called because it's based on the 3 o'clock tangent. There it is. It's called the tangent function. What's the period of tangent? What's the period of tangent? Now, a period is not a starting point and an ending point. A period is an interval or a width of input values. So what is the period of tangent? I heard 2 pi, I heard pi. So, and what was the period? It was defined as the width of interval of the interval of input such that what? One full cycle of output. So where does it start over? How far do we have to go before tangent starts over, is what we're saying. Pi, right? Because we had in the first half circle, we got from 0 all the way to as big as you wanted, then undefined, and then from negative infinity back to 0. That was in pi. And then it started over. So that's a cycle right there. Right there is a cycle, and then it starts over from pi to 2 pi. So we get 2 full cycles as theta goes from 0 to 2 pi. We get 2 full cycles, so therefore the period is pi. Any questions at this point? So it seems kind of arbitrary. It's like, okay, well, why would we want to measure that length? Well, we'll see when it in a second here. We'll see. But let's just go back to our table. So what are possible input values into tangent? All real numbers? Most real numbers, right? But we got a couple problems, right? Where? Yeah, so kind of, yeah. So at pi over 2, all multiples of full rotation past pi over 2, right? So except, say, pi over 2 plus, so we can say 2 pi k, where k is any integer. Okay, so go to pi over 2, and then add as many full rotations backwards as forwards as you like, and that's going to be where the tangent is not defined. Okay, is that all? And also, what? 3 pi over 2 plus multiples of a full rotation, right? Multiples of a full rotation. So k is any integer. So all full rotations from pi over 2, all full rotations from 3 pi over 2 give us problems, so they can't be possible inputs into tangent. And that's where our vertical asymptotes are. Okay, range of outputs. So what different values, what's the range of values that we got for this vertical distance along the 3 o'clock tangent? What's that? Yep, all real. We can get as large positive all the way to as large negative as you want with the right angle. Okay? With the right angle measure, you can get any real number. And we see that in these all possible y values of the graph. You can get everything, if you're looking at all possible y values, for everything from negative infinity to infinity. Okay, so just quickly, when you do tangent inverse in your calculator, we have that same issue that we had with inverse sine and cosine, that now the input is this vertical distance, and if we don't restrict the angles, we'll get many, many angles. Given one vertical distance along that tangent, we'll get lots of angles that would achieve that, right? So we have to restrict the domain again. And so we want to restrict it so that we hit every possible vertical distance once with one angle. And so can you see what range of angles we're going to pick, so that if you pick the vertical, you can pick any vertical distance from negative infinity to infinity, and we get just one angle in return. So what will the range of angles be? Negative pi to pi. What do you think? So that would be from here to here. Yep. It's going to be the same as sine. So when you do an inverse tangent in your calculator, you're going to get an angle in the same range as inverse sine, from negative pi over 2 to pi over 2, because those angles cover every single vertical distance that we could get of that 3 o'clock tangent line. And then we get one angle for every vertical distance that we choose. Okay, so that's our range of the inverse sine function. Negative pi over 2, but this time now we won't get negative pi over 2 or pi over 2. We don't include those because that's where it's undefined, right? Parentheses means not including endpoints. Okay, the input is any angle. That's why we keep getting it repeat over and over. So the input into tangent is any angle. But when you reverse the process, we need to restrict that range of angles for the output. So your output's going to be between negative pi over 2 and pi over 2. Yeah?
I thought brackets meant not including.
No, brackets mean include, and parentheses mean don't include. Yeah. Okay, so now let's look at, kind of start moving towards why this is relevant for us. So the first thing we can do is in the unit circle here, we can look at sine and cosine. So can you imagine a visual representation of sine and cosine right here? So how could you visually represent sine and cosine in this picture? Do you have an image of that? Okay, well, so maybe was your image this? No, it happened. Oh no. Oh, brother. Something got messed up, sorry. Why? What happened? Oh, wait. I know why. There we go. Sorry, I was past 2 pi. That's why. There we go. So your image of sine and cosine should be that. And then tangent is also measured in radius lengths along the 3 o'clock tangent. That's fine. Okay, so what happens if I make this circle bigger? Do we still have sine, cosine, and tangent if I make that circle, say, a little bit bigger, say 1.2? Are those values still sine, cosine, and tangent? Well, it depends. It depends. If you're still measuring those values in radius length, then yes. But if you're measuring all those lengths in now the unit of the axis, say this is 1.2 kilometers, okay? So say this represents 1.2 kilometers. Okay, in kilometers, what is this? This is no longer cosine theta in kilometers. What is it in kilometers? How would you calculate how many kilometers this is? Yeah, 1.2, because what is cosine theta? It's the number of radius lengths, or the fraction of the radius length. So now if we want kilometers, we need 1.2, that fraction of 1.2. Same with sine. So if we're measuring in kilometers, those lengths are now the radius times the number of radius lengths that we are. Similar, same with tangent. So you just got to know what do you want your result in. If you want it in kilometers, then you've got to take those fractions of 1.2 to get kilometers. If you still want it in radius length, then yeah, those are all still in radius lengths. Okay? Cosine, sine, and tangent. So now, what if, so here we are, and let's say I have any arbitrary radius, okay? So we don't know, it's just some radius, something, okay? So we'll call the length of the tangent L. So how can I, and so this is R. Any radius. R is in the units of the or L is in the units of the radius. How can I write L now in radius lengths? How would I rewrite and get this distance in radius lengths? What calculation would I do to get that in radius lengths? What's that? He wants L over the radius. Will that L over the radius give me that thing in radius length? Yeah, because you're asking what fraction of the radius is L. So you're going to take L over R, and that will give us tangent theta. Did you catch it? So whatever length that thing is, in any circle of radius R, to get it in radius lengths, we got to divide by the radius to get how many radius lengths it is. Okay, but what is that ratio the same as in terms of opposite and adjacent? What is L over R in terms of, isn't it by similar triangles, isn't L over R equal to by similar triangles? Opposite over adjacent of theta. Okay, so this opposite over adjacent is our in the right triangle is the ratio that gives us how many radius lengths we are up on the 3 o'clock tangent. So that's our tangent for the right triangle. That's our relationship for tangent. And let's just review what sine and cosine were. In the right triangle, sine is opposite over hypotenuse. And cosine? Adjacent over hypotenuse. And we saw that we're keeping that meaning. All these ratios keep that meaning of number of radius lengths. Number of radius lengths up to the circle. Number of radius lengths right to the circle. Right to the circle. And now number of radius lengths along the 3 o'clock tangent. Okay, anybody have a question? We're cruising, so did you catch it all? Any questions? All right. So this is now coming. So this opposite adjacent then kind of reveals the usefulness of tracking this quantity that we did this along the 3 o'clock tangent. Sine and cosine was it was a very apparent why it was useful, because it gave us locations, right? It gave us coordinates on any circle. This was a little more abstract from the get-go, but now that we see that it's opposite over adjacent, same ratio as opposite over adjacent, we can apply that. So let's do it. Okay, so here is a situation. We're surveying with our little device here, which I forgot what it's called. What is that called? That's what surveyors use to measure angles. Any civil engineers here? It's like an outdoor, but it's there's a name for it. Anyway, so it measures angle. This is called is the angle of elevation. Angle of elevation is the angle that's swept up from horizontal. Angle swept up from horizontal. So we put our instrument here 70 feet from the tree. 70 feet from the tree, and then we measure the angle using this device to the top of the tree. And we got 39 degrees. Okay? And then we note that the instrument, it's measuring from 3.5 feet above the ground. So we want to use a right triangle to solve this and find out how tall the tree is, right? So because we can't, it's very difficult to climb. This is a very efficient way to do this rather than climbing the tree and dropping a tape measure, okay? So much more efficient to use this instrument and use the mathematics. So we need a right triangle that's going to help us solve this. So can you imagine the right triangle that you're going to kind of superimpose into this situation? Can you imagine it? So do you have an image of it? See if you can just think what right triangle would help us solve how tall the tree is. Where will the bottom of the right triangle be? On the ground? Where will it be? Yeah, the bottom will be up here. And so then where will the right angle be? At the tree, right? Okay, so this is the triangle that's going to work for us. So now we need to identify. We have our angle here, theta. Okay? And so now, based on that theta, we need to identify the adjacent, the opposite, and the hypotenuse. So which leg is adjacent to that angle? Bottom is the adjacent leg. Maybe we should ask, where's the hypotenuse first? Yeah, so this is the hypotenuse, and then the other two are legs, adjacent and opposite. So this is our hypotenuse. Okay, so then the opposite is the leg that's across from or opposite from the angle. So now, which do we know? Do we know adjacent, opposite, or hypotenuse? We know adjacent equals 70. What are we trying to find? Opposite's going to help us get the height of the tree. And then we have the angle. So then we ask, which relationship brings together those three things? Which relationship brings together adjacent, opposite, and the one we just did? Tangent of theta. So tangent of theta is opposite or height, right? It's a height measured in the units of the radius, right? Or the number of radius lengths. Yeah. That's what happens when you try to talk and write at the same time. Okay? Opposite over adjacent. So, and we're solving for which one? That's our unknown. So we do tangent of 39. So when you use your calculator, you got to make sure your calculator is set to degrees now, not radians. And our adjacent is 70. So what's the opposite? The opposite is 70 times tangent 39. Let's get an approximation for that. 56.68. So we'll go 56.7. That's that height. Is that the height of the tree? Right. So to get the height of the tree, we got to add down to the ground, and that's our 3.5. Is that 60.2 feet? Questions? Nice, easy example to start with. Anybody have a question on that? So that's the basic premise. You got to superimpose a triangle into your situation, then decide what do you know and what are you trying to find, and then use the right relationship that brings together your knowns and what you are trying to find, your unknown. Can we go on? Okay, so I talked about the angle of elevation. There's also this thing called the angle of depression. It's a little trickier. Students have a little more trouble with this. So angle of elevation, again, angle swept up from horizontal. Angle of depression is the angle swept down from horizontal. Okay, so let's write that. Angle swept down from horizontal. So why do students get messed up with this? Because they put a triangle in, and they're given the angle of depression as a value, and they put a triangle in, and they make this the angle of depression. That's a common mistake that students do. That's not the angle of depression. The angle of depression is the angle swept down from horizontal. So watch out for that. It's a common mistake. That is not the angle of depression. You could find it. You could easily find it from the angle of depression. But that angle of depression is the one swept down. Okay, so let's apply that. So, oops. Okay, try this one. Angle of depression is this one. So you can draw this triangle, but it's not this angle. It's this one. So instead you could draw this triangle. Okay, so the depth of the water is this. We've got the hypotenuse, and we want, is this opposite or adjacent? So we got opposite, we want opposite, we've got adjacent, and we've got angle. Which relationship? Hypotenuse, sorry. We want the opposite, we have the hypotenuse. Sine of theta equals opposite over hypotenuse. And again, we're solving for the opposite. Okay, what I'm going to do is I'm going to keep the video running. and I'm going to work through another slightly harder example. If you want to stay, you can, or if you want to just watch the video. I don't want to encroach on your Thanksgiving break. So have fun, be safe. Yes. Shortened. Here we go. So here's the last problem, is finding the height of the Matterhorn. How tall is the Matterhorn? Where is the Matterhorn? Switzerland? Yeah, Disneyland. Does anyone know where the Matterhorn is? Switzerland, I think, right? Switzerland. Okay, so here's what they do. They stand over here, and they get the angle of elevation as 30, and then they get 1,500 feet closer, and they get the angle of elevation of 35. And so from that information, we can figure out how tall is the Matterhorn. Okay? So what can we do here? So this is an unknown length, right? So call it y. X or y. Y would be great. Okay? X is usually horizontal, so let's call it x. So then, what are we bringing together? Of hypotenuse, adjacent, and opposite, what are we bringing together to solve this problem? Which two of those apply?
What do we know?
We know that this angle is 30, and this angle is 35, and the distance between those elevation points is 1,500.
Let's work with the most left triangle first to get that, or one of the left.
So my question was, what do we have to work with? Are we working with hypotenuse, adjacent, opposite? Which of those?
Opposite and adjacent.
Opposite and adjacent. The hypotenuse doesn't really come into this, right? So we're working with adjacent lengths, and the opposite is our unknown. Okay, so which is that? Sine, cosine, tangent. Tangent. So we can write the tangent of 35 is what? X over, let's call this the height. Isn't it x over h? No, it's not. H over x, opposite over adjacent. And then we got tangent of 30. What's tangent of 30?
H over x plus 15.
H over the whole adjacent side, which is x plus 1,500. Does it make sense so far? So we got two right triangles that both have the same opposite side, which we're calling H. The one with angle 30 has an adjacent side of 1,500 plus x in length, and then the one with angle 35 has an adjacent side length of x. So we can set up tangent as opposite over adjacent for both of those. Okay, so now we're going to use these as approximations. We're going to use approximations, so our answers will be approximations. This won't be an exact. This will be more like an engineering exercise rather than a mathematical exercise. Okay, so because these are going to be infinite decimals, so as soon as you pick a decimal off, you get an approximation. But that's all we would be doing in the real world anyway, right? We would just be getting a close approximation. All right, so we can solve both these for h, and then tangent of 35 times x would equal tangent of 30 times x plus 1,500. And so with approximations for tangent of 30 and tangent of 35, we can use algebra and we can get x, an approximation for x. And then with that approximation for x, we're home free. What is h? H is x times tangent of 35. And then we get approximation for the height.